To understand what AP statistics is, we first have to look at what it really is about. Many people find it as simple as just percents or probabilities. But there is much more to it. Statistics is about understanding and interpreting data. Median is a simple way to measure the center of data. Median is simply the middle point of the data. There must be an equal amount of data both to the left and to the right of the median. And if there isn't a middle point, it is simply an average of the two middle points of the data. For example, in this data, the median is 5 because it is the middle point. And in this data, 12 is the median. Because it should be reorganized as this, making 12 in the middle, it should become more clear. Mean is simply a different word for average. What is average? Average is the sum of all points divided by the number of points. For example, in this list of 11, 12, and 13, 11 plus 12 plus 13, all divided by 3, equals 12, therefore making 12 the average. Mode is simply the most common data point. In this data, 2, 3, 5, 7, and 7, the mode is 7 because there are more 7s than any other number. Just as here, the mode is 2. In the data, 1, 2, 2, 2, 3, and 4. Spread is simply measuring how spread out a set of data is. Range is a way of measuring spread. It is simply the maximum point minus the minimum point. In this way, the range is the total distance that all the numbers encompass. Standard deviation is just the average distance away from the mean. In this way, a larger standard deviation means that stuff is farther away from the mean and more spread out. The standard deviation is also the square root of the variation of a set of data. What is the variation? Well, it is the standard deviation squared. In order to understand the next measure, the interquartile range, or IQR, we must first know what a box plot is. A box plot shows the minimum point with an end line as such and the maximum as such. It shows the median, or middle number, with the line in the center of the box. If we remember back to what the median really is, it means that half of the data is below it and half of the data is greater than it. In this way, median is what is known as the second quartile. Well, what is the first quartile? The first quartile has 25% of the data in front of it and 75% of the data after it. And the third quartile has 75% of the data in front of it and 25% of the data after it. So the amount of data between the point of minimum and the first quartile contains 25% of data. The amount of data between the first quartile and the median contains 25% of the data, and the amount of data between the median and the third quartile also contains 25% of the data. And as you can guess, the amount of data between the third quartile and the maximum also contains 1/4 of the data. The IQR is simply the distance between the first and third quartile. In this way, the IQR is the interquartile range, or between quartile distance. What is an outlier? Well, an outlier is a point that is very far off from the rest of the data. How far off? Well, at least 1.5 times the IQR away from the third or first quartile. To find this, simply take your IQR, multiply it by 1.5, and add it to either the third or subtract it from the first quartile and see if your number lies outside of this range. If it does, your point is an outlier. Outliers are not included as a minimum or maximum on a box plot. It is simply included as a dot separated from the rest of the data. It is important to know how outliers affect our center, such as mean, median, and mode. If a point is really far away from the center of data, it will skew the mean a lot. This is because the mean takes into account how extreme the point is. 0, 1, 3, 4, 4, 6 results in a mean of 3. If we were to take this data and add an outlier like 200, we would get 0 plus 1 plus 3 plus 4 plus 4 plus 6 plus 200, all divided by 7, equals 31.14. You can see the number 200 has greatly skewed the mean of this data to not accurately represent the rest of the data at all. If instead we took the median of this data, we can find that the median is less skewed by this large outlier. 4 is the median, or middle point, because there are 3 points on both sides of it. Because the median was affected less by outliers than the mean, it is more robust than the mean. Our last measure, mode, is simply the most common number. In this way, an outlier would have no effect on our mode. This is because outliers are by definition uncommon, and therefore mode is the most robust out of all the data. Of the data, 0, 1, 3, 4, 4, 6, 4 is the most common. If we were to add 200, the data 0, 1, 3, 4, 4, 6, 200, 4 would still be the most common, keeping our mode. Throughout all of this, you need to remember to explain everything with context. If a problem were to ask you what piece of data was an outlier on the graph, you wouldn't answer 50. You would answer the man with 50 shoes. Context is always needed for each problem and explanation along with it. This is an example of a line of best fit plotted onto some points. The line shows the relation between the number of customers in the checkout line and the time it takes to finish. Now this chart also gives us a computer output. This computer output has various assortments of data. The first thing the chart tells us is the line of best fit. The constant number tells us the y-intercept of the line, and the customers in line tells us the slope. This is easy to remember because the customers in line number is multiplied by the x, and the x value is the number of customers in line. The SE coefficient is simply the standard error of each of the values. Standard error is simply the standard deviation of the sampling distribution. Don't understand? The sampling distribution is simply the total number data we get in all our tests. It isn't the standard deviation of all the individuals in a given test, but the standard deviation of this individual test from all possible tests. In this case, the standard deviation of the slopes that we get of this 174.4. The S in the bottom left corner tells us the standard deviation of the residuals. Residuals are the difference of points from the LSRL. So this number just tells us the average number that our LSRL is off from the real data. The R-squared value at the right of this is the coefficient of determination. This value tells us the percent of the variation in the Y value that can be explained by the X value. You need to keep this phrasing. It is always the percent of the variation in the Y value that can be explained by the X value. Just input the name of the Y value in and the X value, and then you'll have the interpretation of this R-squared value correct. This R-squared value can be used to determine how great the association is. If there is very little association, we can assume that the X value has very little effect on the Y value. Another thing to keep in mind is that if the data does not fit the shape very well, it may be a different type of association besides linear. For example, it could be exponential. To see this, take the Y value and replace it with the natural log of the Y value in your LSRL model. If it is a power model, then take the natural log of both the X value and the Y value. In order to know which model works best, just compare the R-squared value. The one with the higher R-squared value will always fit better. Imagine we are asked to compare the distribution of CH5OH peaks and HCO peaks in the atmosphere. In order to compare this, we must compare 4 different measures: shape, center, variation, and outliers, and then put all of these into context. The shape of HCO is approximately normal because of how well it fits with the normal curve. The shape of CH5OH, however, is extremely skewed right. To compare center, we can use mean, median, or mode. In this case, the CH5OH has a mode of 0.8 km per second, while HCO has a larger mode of approximately 2.8 km per second. Note in this that you need the context to describe which is both by comparing them. By using the word larger and also using the unit that the variable is measured in. To describe variation, we must compare either the variation, IQR, or standard deviation. The IQR of HCO is approximately 3 km per second, while the IQR of CH5OH is much lower, at approximately 1.2 km per second. For outliers, you must test to see which points count as outliers by taking 1.5 times the IQR away from Q3 and Q1, and then list what the outliers are. HCO has outliers at 8.8 km per second, and CH5OH has outliers at 8.2 kilometers per second. Analyzing charts is something that most of us are familiar with. A note to make is that in a pie chart, all data must add to 100%. If there is ever a problem asking if the data is appropriate for a pie chart, you must test this. Another chart to look at is event diagram. The probability represents that only event A happened, and this probability represents that only event B happened. This probability represents that event A and B happened, and this probability represents that neither happened. All of the probabilities must add up to 100%. If we imagine a scenario in which A and B cannot happen, the events are known as mutually exclusive or disjoint. Another thing to know is that a complement means that it has not happened. If this circle represents that A has happened, then the space outside of this circle represents the probability of the complement of A. Another thing to know is unions versus intersections. A union of A and B is the probability of A or B happening. It represents all of these added together and is represented by a U. The intersection of A and B represents the probability of A and B happening, and can easily be remembered by being the intersection of these two circles. It is also represented by an upside down U. This problem presents us with a given sample of people with schizophrenia. It labels it as a point to find evidence for association between them. It is key to note this problem labeled it as association because that means that we would use this labeled for a chi-square test for association. In order to know if a problem is a chi-square test for association or a chi-square test for homogeneity, you can look inside the problem, like we just did, and analyze how the data was collected. If the data was collected as one big whole group and then split into different categories like gender, you can do a chi-square test for association. If the data, however, was first split into groups and then randomly collected, you must do a chi-square test for homogeneity. Now that we have determined what kind of test we must do to solve this, we must choose our alpha value. The alpha value is also known as our significance level. This is because it is the probability at which our answer will become significant enough to reject a null. Don't worry too much about this definition for now, we'll come back to it later. We just choose an alpha of 0.05 because that is a standard. We must also write our null and alternative hypothesis. One thing that we are trying to prove is that there is an association between gender and schizophrenia. This would be our alternative hypothesis. Why, you might ask? In the test, we are trying to prove our alternative hypothesis by disproving our null hypothesis. If it is extremely unlikely that we would have gotten these results if there was no association, then there probably is an association. Therefore, we will assume that there is no association and try to show how unlikely this result is. We categorize all the steps that we just did as the state part of the problem. We have stated the problem we are doing and have set the outlines for the rest of the test. Next, we must do the planned proportion. The planned proportion is where we test conditions for a test. There are the same conditions for both the chi-square test for association and the chi-square test for homogeneity. Random and large sample. The problem states that this is an SRS sample of 207 men, so therefore we know it is random. An SRS sample is a random sample by which each individual in the study is assigned a number and is randomly chosen from the number table. And an SRS is also called a simple random sample. In order to test that we have large sample size, we must first gather the expected values. Expected values are expected values for this data if there was no association. The expected values are gotten by multiplying the column total by the row total and then dividing by the total. If all expected values are greater than or equal to 5, we have a large enough sample size. Write conditions met below because all conditions are met. Now that we have met all of our conditions, we are on the do portion of the test. In the do portion, we find the test statistic and probability of getting a result this extreme or more extreme. Take all of the values in our table and subtract them from their expected values. This is the difference table. Then square these values and divide them by their expected values, and add them all together. You will have our chi-squared value. This value, however, means nothing by itself. Next, we must determine our degrees of freedom. The degrees of freedom is the number of columns minus 1 times the number of rows minus 1. In this case, we have 4 columns and 2 rows, so we take 2 minus 1 times 4 minus 1, which equals a degrees of freedom value of 3. We can then use a chi-squared statistic and the degrees of freedom to determine our p-value. A chi-squared value of 10.88 and a df of 3 results in a p-value of 0.01. In the conclude portion, we interpret the probability that a result this extreme will happen. In this case, we are assuming that these are truly independent because that is our null hypothesis. We are then finding the probability that we get a result that is very extreme, and if the probability is really low, lower than our alpha, we would say that this would be unlikely given our null is true. We would then reject the null and conclude the alternative hypothesis. Keep in mind, you can never accept or prove the null hypothesis. You can only disprove or fail to disprove. In this case, we get a p-value of 0.01, which is less than our alpha of 0.05. Therefore, we will reject our null. This is because this result or result more extreme would only have a 0.01 probability of happening if the null was true. This is more unlikely than what we set our alpha to be, 0.05, so we will reject the null and conclude the opposite, our alternative hypothesis. We conclude that there is association between age and gender. In a chi-square test for goodness of fit, we would just have one row of values versus two or more, and we would simply find the difference by subtracting them from expected values. Also in a chi-square goodness of fit test, we would also have to test independence by making sure the values are 10% or less of the population being tested. In this test, we are finding the portion of people who are unemployed. It is therefore a z-test for proportions. We will once again choose an alpha of 0.05. Our null hypothesis is what we assume to be true, that the unemployment is in fact 8%. Our alternative hypothesis is that the unemployment is not 8%. The condition for a one-sample z-test for proportions are random, independent, normal. The sample is random because they took an SRS of 200 residents in the town. The sample is independent because this sample contains less than 10% of all the possible people surveyed, because the problem states that there are more than 3,000 residents in the town, and 3,000 times 10% is 300, which is still greater than our sample of 200. This is normal because in any z-test for proportions, you must check that the number of theoretical successes is greater than 10, and the number of theoretical failures is also greater than 10. This is known as NP is greater than or equal to 10, and N1 minus P is greater than or equal to 10. This is because N is the sample size and P is the probability of success. Therefore, this shows theoretical amount of success and amount of failure. In this case, both conditions are met. In order to find our z-statistic, we take the difference of our statistic and the parameter divided by the standard deviation of the parameter. What is a statistic or parameter? A statistic is a form of test like ours. It is the proportion that we get from a sample, in this case, 22 out of the 200 residents. A parameter is the true value, or what we assume to be the true portion, in this case 8%. By finding the z value, what we are doing is finding how many standard deviations away our statistic is from the proportion. The key trick to this is knowing that our sample distribution is normal, like what we tested above. Once we know our sampling distribution is normal, and we know how many standard errors away our statistic is, we can find the probability of getting a statistic this extreme. In order to find the standard error of a portion, we would take the probability, multiply itself by 1 minus itself, and divide by the number of individuals in the test. Then take the square root of all of that. Keep in mind this is the standard error of the problem because it is the standard deviation of all of the possible solutions. It could also be called the standard deviation itself because of that. This results in a z-score of 1.56. Draw this on a standard normal curve next, with the mean 0 and standard deviation 1. Then plug in the z-score into a z-score table and find the p-value. Then interpret it just as we did in the chi-square problem. We also need to multiply our p-value of 0.059 by 2 to get the true p-value, because this is a two-sided test and we are testing to see if it's on either side. Because our p-value is 0.117, our p-value is greater than our alpha of 0.05, so we fail to reject our null. If this was with means instead of proportions, the standard deviation would have to be either calculated with a calculator or given to you. The check for normalcy would just be n greater than 30 or that our sample size is greater than 30. If it was not greater than 30, you could also check to see if it's robust. If n is less than 30 but greater than or equal to 15 and the distribution has no outliers and no strong skewness, you could determine that you have met the normal condition. If n, however, is less than 15, you must check that there is no skewness whatsoever and that there are no outliers. Then the conditions will also be met. For doing a t-test, you would need to determine the degrees of freedom by taking the sample tested minus 1 and then finding the p-value of it on a table or in your calculator. This test is also called a t-test for means. Draw a curve for a t-curve instead of a normal curve for a t-test. A two-sample z-test for proportions is a test to check that two proportions are equal, not equal, less than, or greater than. In this case, testing to see that both the near signness for the years 2000 and 2015 are equal. In this case, we will define P0 as the percent from 2000 and P15 as the percent from 2015. We put the triangle hats over P to show that this is the sample amount and not the true value. Our null hypothesis, or what we assume to be, is that P0 equals P15. The alternative then is that P15 is greater than P0 because of the context of what was suggested in the problem. Once again, we will set our alpha to be 0.05. In our one-sample z-score for proportions, we took our statistic and subtracted the parameter from it. In this two-sample z-score, we simply subtract both sides. In order to find the standard deviation, you must take the lump probability. In order to find the lump probability, we are going to take the total successes divided by the total trials. In this case, 132 plus 228, all divided by 400 plus 600, equaling a 0.36 for our lump probability. We then have to find the lump standard deviation. This is by using our standard deviation formula for probabilities, which is probability times 1 minus the probability, all divided by the number of trials, and then take all of that and square root it. In this case, 0.36 times 1 minus 0.36 divided by 400, and 400 in this case is the smallest sample that we have used in getting our lump sum. We use the lump sum standard deviation because our null hypothesis, which we assume to be true, says that the probabilities are independent. If they are in fact independent, then there is only one standard deviation for both statistics. This is because the standard deviations for a proportion can be determined by the proportion. If we assume that proportions are the same, we must assume the standard deviation of the proportions are the same. We only assume this for the null test, where we can assume the proportions are equal. Take the difference of 132 over 400 minus 228 over 600, which is our statistic for difference. Subtract from our parameter. This is 0 because we're assuming that there is 0 difference because we assume that the proportions are equal, and then divide all of that by the square root of the 0.36 times 1 minus 0.36 over 600 plus 0.36 times 1 minus 0.36 over 400, and all of that gives us a z-score of 1.61, which gives us a p-value of 0.053. So we would interpret and be unable to reject our null. If this were a two-sample t-test for means, we would have to check the t-test condition. We also only have to take the difference in means over the standard deviation combined of means. The standard deviation for each mean would have to be given to you, or data would have to be given to you so that you could determine that. In this case, in order to get the combination of standard deviations, you must just add the variations. In this case, we square each standard deviation. Then we take each standard deviation and divide them by the sample size they correspond to convert them to standard error. Then to convert them back to standard deviation from variation, we square root it all again. Then we find our t-score. Our degrees of freedom is our lowest sample size taken of any statistic minus 1. There are several different types of design a study can have. An experiment is a study in which we give the individuals a treatment and observe the effects. This treatment can be anything that we give them in hopes of observing the effects. It could be medicine or it could be a type of bug spray. As long as the study involves giving the individuals the treatment and the effect of the treatment is what is being tested. A control is a thing that an experiment is held to. It often has a placebo. The control is a sample with no treatment but is still observed. It is what the treatment can be compared to in order to see if the treatment was effective. An observational study is just like an experiment, but a treatment is not assigned. It could be a study where people with cancer are given IQ tests and where people without cancer are given IQ tests. The difference between this and the experiment is that we didn't give the people cancer. We merely took people who already have cancer. In observational studies, we can only find correlation, not causation. This is because we did not cause the sample to have a given condition, and therefore cannot test it. However, in the experiment, we caused the condition by giving them the treatment, and therefore in experiments, we can conclude causation. If you ever have bias or undercoverage in a method of sampling or gathering data, you have bad data, and it should not be used. An example of undercoverage could be only surveying people with landline phones about how they feel about the economy. This would undersurvey everyone without landlines and could lead to an inaccurate conclusion. A biased sample is a sampling method in which the sampling method has a different theoretical mean than the true mean. Biased sampling methods are to be avoided over everything else and shouldn't be used. Also to note is that conclusions of a sample can only be applied to the group of the people that the sample was taken from. If a sample is only sampling people from New York, they can't conclude everything about the whole United States. A single blind study is a study where the participants don't know which group they belong to. This helps eliminate bias. For example, if you hold a study on the effects of a new drug, people might arbitrarily feel better if they take the medicine, regardless if it works. To eliminate this, we would give the control group a placebo, and then the participants wouldn't know which sample they were part of and therefore make the sample less biased. A double-blind sample is like a single-blind sample, but the experimenters testing the sample also don't know which treatment they are giving the patients either. This helps eliminate any bias that the experimenters might have in interpreting the sample's data. For example, this could be not telling the doctors treating and reporting on a patient if they are giving them the placebo or not. This also helps eliminate bias. In observational and experimental studies, the only difference was if there was a treatment that we applied or a condition that we observed. In one we have to test IQ, and in one we have to give medicine. The only difference is that in an observational, the thing we are testing is already the prevalent condition. In a survey, however, we don't get to test anything at all. We merely just ask questions. Unlike the observational study, though, we cannot test anything ourselves, and can therefore not conclude causation. In a matched pairs design, you can have the sample going through two treatments. For example, you have someone take both a math test with mints and a math test without mints. Because you have the same sample taking both of the tests, you are actually not doing a two-sample test. It is just a one-sample test. What you really do is not take the difference of the means from each sample, but the mean difference of everyone for a test, and therefore it would be a one-sample distribution. It is mean difference because you take the differences and then you find that's mean. A block design is a design of an experiment where you divide the sample into different groups that you survey differently. For example, you test 100 red leaves and test 100 blue leaves and record the results separately. A stratified sample is the same as a block design, but is for an observational study and not an experiment. A conditional probability is a probability given some condition. For example, the probability that someone is male given that they are right-handed. In order to determine this, let us look at a two-way frequency table of data. In order to find this probability of male given right-handed, we take the total possible to be selected, all right-handers, and put it on the denominator. And we take all possible to succeed, right-handed males, and put it on the numerator. Now let's imagine that we want to find if being right-handed and being male are independent. Independent just means that they are not related, and the probability would have no effect on each other. In order to do this, we merely take the probability of being male, which is males over the total sample, and compare it to our probability of being male given that they are right-handed. In this case, 23 over 50, or 0.46, is not equal to the 20 over 43, or the 0.465. Therefore, we can conclude that there is an association and that they are not independent. A confidence interval is an interval that we think a statistic is in to a certain confidence level. A confidence level can and must always be interpreted as a level where if we were to repeatedly make confidence intervals, something percent of the intervals would have the true mean in it. For example, a 90% confidence level would, if repeated to make confidence intervals, have 90% of the confidence intervals contain the true mean. In order to calculate a confidence interval, just take the sample mean of a value, in this case 15. Then what we do is we take plus or minus the standard error times the critical value. The standard error would be found to be the same as we found it for all the other problems. However, it is important to know that we do not use lump sums for confidence intervals. Now that we have given a standard error, you might be asking what critical value is. The critical value is simply the multiplier for the type of test we have and the confidence interval. Finding the critical value is simple. If we have a 90% confidence interval, we know that there must be 5% of the data on either side of the curve. Therefore, we take an inverse z of 5%, and then that is our critical value. If it was a t-score, we would have to take an inverse t-score with the same degrees of freedom as if it were used to calculate standard error. In this equation, the whole right side is known as the margin of error, because it is how much we can be off from the mean. The next step is simply to calculate and simplify the range. If you ever need to interpret a confidence interval, it is simply the range that we are blank percent confident the true mean lies within. If you have a TI Nspire, using a calculator to help find p-values from chi-squared, z, or t values is pretty easy. Simply hit the menu button, then statistics, then distributions. It then has a list of all kinds of distributions. Among them you will find binomial and geometric. A binomial distribution usually ends up being normal. A binomial distribution is a distribution by which you repeatedly try a chance a set number of times. For example, it would be finding the average number of heads when you flip a coin 5 times. The conditions are binary, independent, normal, and success rate. Binary just means either succeed or fail, and no in between, which is obvious, either heads or not. Independent just means that one test does not affect the other, and sure enough, one coin flip does not affect the other. Normal is just the sample size is greater than or equal to 30. Success rate just means that there is a set success rate, in this chance 50%. This case can be used to determine for a test, just like a t-test for means or a confidence interval. The average of a binomial distribution is simply the probability of success times the sample size, and the standard deviation is the sample size times the probability of success times 1 minus the probability of success. Another way to find a specific value for binomial is just take the probability of success raised to the number of successes necessary for that value, and the probability of failure raised to the number of failures necessary for that value, and then multiply the number by the combinations of that value. To use combinations, just go to Menu Probability Combinations on a TI Nspire or use this formula. Geometric has the same conditions as binary, but instead of having a set number of trials, it has trials until success. It is very right skewed and not normal, but if you want to find the probability of a certain value of a geometric distribution, simply take the probability of success, raise it to the number of successes required, and multiply by that probability of failure. If you want to find a range, add them all together or subtract the complement.